Previous video, we talked about tracking a vehicle and using a Kalman filter to do that. Um, and really anything with position, velocity, and acceleration is the same kind of problem as tracking. Um, we had a couple models for it. The dynamics were captured in the phi matrix of the state space model of the used for the Kalman filter. If you sampled fast enough, if your time between samples was very small compared to how fast the thing changes. Here was your phi matrix, all constants. It's just a function of your time step. And if that time between samples was relatively slow compared to how fast the thing changed, you'd use a state vector that has just two components. This one has three components. This one just has two components. So you would use this phi to help you project, propagate from this time to the next time. And then what do you do once you get a measurement at some time, used to call K, but you get a measurement and we're only measuring position. So this is just a scalar here. It's the position minus what your estimate of position was prior to getting the measurement. So it's this simple update with these gains. Now with the Kalman filter, these gains changed every time. And we had to go through the pain of computing it every time. What if you didn't? What if you wanted a simpler way to do it? Just say, I'm going to pick, there we go. I just want to pick these gains ahead of time and just keep them constant so that they don't change every time step. What should you use for those gains? One method is steady state Kalman filter gains. And we have a way to know what those are. If you do all that, you get simple scalar equations, so simple you could do it in a spreadsheet. I guess it's still a computer. It's simple enough you could do it by hand, although it would get tedious if you had a lot of measurements. But these three equations up here, well, this over here is the three state variable approach and this two state variable approach. And these guys are called the alpha beta gamma filter over here, and this is called the alpha beta filter over here. I guess for some historical reasons, people started analyzing these using alpha and beta to gamma to describe your gains. These first three equations up here are just implementing this phi matrix. These three equations down here are implementing these three equations. If you were using this two-state variable thing, you don't have the top two. And that corresponds to what happens over here. Anyway, very simple alpha beta filter could be viewed as a steady state Kalman filter. It's something just as position, velocity, and acceleration. It can also be analyzed classically, like a control system thing. It's a digital filter, but you could look at it and characterize it in terms of settling time, maximum overshoot, and other classical measures of performance that we get out of control systems. But if you wanted to pick your optimal cases based on the Kalman filter, here's some formulas, trust me. You can just tune it with one of those three guys. You pick an alpha, these tell you how to pick the beta and the gamma. And just recall, I talked about the Riccati equation before. It's a way to get this error covariance matrix all in one equation. And if you solve that equation for this piece of SS superscript, you can compute the gains in the PSS steady state error covariance without the superscript. meaning right when you get right after you process a measurement. And if it was a scalar problem where the phi and h were just scalars, you could solve it by hand, and we did that before. You get a quadratic equation. This Riccati equation just becomes a fairly simple quadratic equation. Beyond that, you probably need a computer. MATLAB does it. And here's the simple command. You spend most of your lines of code just defining the matrices you go into. MATLAB is set up to solve the Riccati equation for the optimal control problem. So we have the optimal estimation problem is a so-called dual to the optimal control problem. So we're doing estimation, so we have to kind of switch some of the matrices. I'm not going to get into that deeply here. And speaking of which, in control systems, you have this system here. You have feedback control. If you have access to the entire state vector, you can do what they call state feedback control. And you could come up with an optimal gain K that optimizes the performance of the system, feedback system. What if you don't have access to the entire state variable X? You have some Y, which could be a subset, Y equals H times X. So some kind of linear combination of the state, and maybe incomplete, and maybe a noisy version at that, because of measurement noise. If you use as an observer a Kalman filter, which says you take what you measure and estimate this state vector, and then use that estimate of the X in this system, you end up with the overall optimal control system. You used an optimal estimator, the Kalman filter, for the estimating part, estimating the X. And then you used the optimal control gain K for the feedback part. So a Kalman filter is part of an overall optimal control system. And one last little tidbit on the Kalman filter. I had always, I believe, asked my students to just go online and show me one application that you found of a Kalman filter or extended Kalman filter. We'll do extended Kalman filters in the next module. And it's a pretty eclectic list. It's not just tracking a vehicle. Indian stock market, GDP, frequency of brain neuron fires, soil moisture, anxiety detection. It's used, or they attempted to use, on a lot of things. It's not just gas spring damper systems and vehicles. And I think now that that's the last I want to talk about Kalman filters until we get to the extended Kalman filter in the next module, which is for nonlinear systems.